Okay, I will share you the link. So when is your exam? In February? When?
So, you were not audible.
But so your exam will be in February, right? Gate exam. Okay, okay. So we have 1 month then. Okay, so let's start gradually, then others will join. So today I will be discussing some topics from Kinetics chapter, some important topics and some expression from Kinetics chapter. Mainly we'll discuss some expressions and some ideas like from transition state theory to collision theory and different types of complex reactions like reversible reaction, stepwise, parallel reaction, like this. Okay, so if you have any doubts in the meantime, you can just ask. Okay, so let me just share my screen. Okay, kinetics. So am I audible properly?
Yes, sir.
Okay. So first, kinetics is basically to find out the rate and the mechanism of any chemical reaction that is happening. So mainly we are trying to find out here the rate and the mechanisms, like how fast or how slow the reaction is happening and how the reactant molecules are participating to form the product. So the main mechanism. So there are actually various types of reaction, and we can categorize it like unimolecular reaction, bimolecular reaction, etc. So basically elementary reaction is, so there are mainly two categories: elementary reaction and complex reaction. So elementary reaction means the reactions which are happening in a single step. So this is basically a single step reaction. So here no intermediate is formed. So if you just schematically draw, let's say this is reactant molecule and this is product molecule. So from reactant to product, it is like happening like this. So no intermediate is forming here. So just a single step reaction. And for elementary reaction, you know, in the rate expression, the order of the reaction is equal to the molecularity of the reaction, right? So for unimolecular reaction, like let's say for unimolecular reaction, unimolecular reaction means there is only one molecule is participating in the reaction process. Let's say A to P. So this is unimolecular. Now let's say this is a balanced equation from A reactant, this is reactant, and this is product molecule. Now in the balanced equation, let's say 2 mole of A is reacting to form product molecule of B. Now if you write down the rate equation here, that will be just rate of disappearance of A molecule, means d of A dt, minus sign because it is disappearing. So product is forming and reactant is disappearing, that's why it is minus. So concentration is decreasing, concentration of A is decreasing, so that's why the minus dA dt, which is the rate of disappearing of A molecule, which will be equal to some rate constant times concentration of A square, right? So this will be the rate equation for the for this type of reaction. Now this is the rate constant, and this is actually the order of the reaction, right? Order of the reaction. That means the rate is actually varying with the to the power square concentration of A molecule. So now for unimolecular reaction, this order of the reaction is equal to the molecularity of the reaction. Molecularity. So molecularity means the number of molecules that are participating in the reaction process. So here in this reaction, you can see here in the balanced equation, 2 mole of 2 A molecules are participating, right? So the molecularity for this reaction is 2. Now since this is a unimolecular reaction, one type of molecule is participating, that's why the order of the reaction is also equal to the molecularity of the reaction. So this is actually important. The second, you can just talk about the bimolecular reaction, trimolecular reaction, like this. So these are very complex reaction. Bimolecular reaction means 2 types of molecules are interacting with each other or participating to form the product molecules, like A plus B to product molecule P. So this is bimolecular reaction. Now the second category is a complex reaction. So elementary reaction is the first category, and the second category is the complex reaction. So complex reaction basically the reactions in which the many steps are there. So many intermediate steps are there. So that those types of reaction you can call the complex reaction. Like from A to product P. So if the product is forming by a single step, then we can call the unimolecular reaction. But if it is forming through multiple intermediate steps like this, from A to B, then B to C, then C to P, so multiple intermediate steps are there, right? The first step, this is the second step, this is the third step. So this type of reaction we can call the complex reaction. So multiple intermediate steps, more than one intermediate steps are there. Now for complex reaction we can categorize it different types, like mainly 3 categories. One is consecutive reaction or stepwise reaction. Stepwise or consecutive reaction. Second is actually parallel reaction. Third is reversible or opposing reaction. So first let's discuss first for consecutive reaction. Consecutive So stepwise or consecutive reaction means so reaction is happening in stepwise fashion. Like consecutive means, let's say from reactant molecule A, first it is forming product let's intermediate B molecule, then from B to C. Okay, so consecutive means it is happening in a stepwise fashion. So from A to B, then B to final product C. So that's why we are naming it the consecutive or stepwise reaction. Now let's say first at time t equal to 0, only reactant molecule is there, right? So let's say the initial concentration of A molecule is A0. So here A is the reactant molecule and C is the final product molecule. This is final product, and B is the intermediate product or intermediate step in. So at time t equal to 0, the concentration of B and C will be 0, only the concentration of A will be there, which is A0. And at time t, so from A molecule will be disappearing and the B and C consecutively will be formed. Now let's say for this step A to B, the rate constant is K1, and from B to C, let's say the rate constant is K2. Okay, now at time t, so the total concentration of A plus B plus C will be just A0. So this condition has to be satisfied, right? So at time t equal to 0, the total concentration is A0, and at time t, sum of all concentration of all three molecules A, B and C will be the initial concentration of A0. Now first initially there will be no B and C, and then with time the B and C molecule will form. Now let's say K2 is very greater than of K1, right? Let's say this is the condition, first condition. That means the B to C reaction, K2 means this the rate constant for this step. So B to C reaction is happening very fast compared to the A to B reaction, which is the rate constant for this step is K1. So this condition means this. That means if you draw the graph here, that means when at time t equal to 0, no B and C was there. With time A molecules are disappearing to form product B molecule. So at time t, with time first A to B molecules are forming, then the B to C step rate constant is very fast compared to the A to B step, right? That means when the B molecules are forming, it subsequently forming the C molecule, like more or less simultaneously. So that's that. So K2 is very greater than K1. That's it. Whenever the B molecules are forming from A molecules, the B molecules are actually forming the C molecules simultaneously due to the K2 greater than K1. So if you just plot this, so first there will be at t equal to 0, there will be just A molecules, no B and C. So it will decay like this with time. Okay, now first there will be just A molecules, then with time A molecules are disappearing to form the product B molecules. So with time the concentration of B molecules will increase. So at t equal to 0, the B molecules concentration of B molecules is 0. With time the concentration of B molecule rises, right? Now whenever the B molecules are forming, simultaneously the C molecules are also forming. So concentration of C molecules will increase with time also. So it will again, after increasing some amount, it will reach a maximum, then it will decrease again. Why decrease? Because it is forming C molecules. So first, initially at time t equal to 0, the concentration of C was 0. Then with time, B molecules are forming, then from B, C molecules are forming. So that's why with time the concentration of C will also increase like this. Okay. Okay. Okay, so this is concentration of C. This is concentration of A, and the green one is concentration of B. Okay, so this is the plot for a consecutive or stepwise reaction, or for a consecutive reaction. So this is the reaction time, so this is time, and this is the concentration. Okay, so first A molecule will decrease, then B molecule will rise, concentration of B molecule will rise, and after reaching a maximum, then B molecules will also decrease. So that's why the C molecules will increase again, like from in here the C molecules is increasing. Now at any time, if you just at any time, the sum of our all three concentration will be equal to A0 at any time. This condition has to satisfy. Okay, so this is the plot for consecutive reaction, and it is important quite. Now another important thing from the consecutive reaction is the steady state approximation. Steady state approximation. So steady state approximation is, let's say let's consider a reaction like this from A to B to C. So this is the final product, and this is reactant molecule. This is intermediate step or intermediate product. Now we are considering, let's say this is the rate constant for this step is K1, rate constant for this step is K2. Let's consider K2 is very greater than of K1. That means the rate constant for this step is very far or very large. That means this step is very fast compared to this step, A to B step. That means whenever the B molecules will form from the A molecules, the B molecules will simultaneously form the C molecules. So the intermediate, here it is B, is not stable. So it is transient. Transient means the lifetime of the intermediate B molecules is very small. That means whenever it is forming from the A molecules, it simultaneously form the product C molecule. So the lifetime of B molecule is very small. So that's why we call the intermediate is very transient. Now that's why, due to the transient nature, so with time the concentration of B molecules will not change, right? So let's say first at time t equal to 0, the concentration of B was 0. Now with time, whenever the from A molecules the B molecule is forming, it's simultaneously forming C molecules. Next time A molecule from A molecules to B molecules are forming, then it's simultaneously forming the C molecules. So with time it seems that the concentration of B molecules are not changing, so it is becoming like a constant. So that's why we call it so concentration of B molecules reach kind of steady state. So at this state the concentration of B molecules are not changing much with time. So steady state means the concentration is not changing much with time. That means we can say that d derivative of concentration of B with respect to time will be equal to 0. This means, this condition means this: time derivative of concentration of B is 0. That means the concentration of B is constant, right? So this is the steady state approximation. So for any intermediate, any transient intermediate, that means when the lifetime of intermediate is very small, we can apply this steady state condition or approximation, and by applying the steady state approximation we can get a proper rate equation for a more complex type of reaction, right? So we know that, like, let's say very complex reaction from A to B, then B to C, then B to D, then C to E, then D to also E, then E to P, let's say. So this is reactant molecule, this is final product molecule, and these are the intermediate steps. So this is a very complex type of reaction, so many steps are there. So these are all intermediate, right? B, C, D, E. So let's assume that all these intermediates are transient. That means the lifetime is very small. So you can apply all the steady state approximation here, like dB dt equal to 0, dC dt equal to 0, like this. So with these approximations we can get a very small or very convenient rate equation for this complex reaction, like dA dt rate equal to some rate constant k times some convenient equation. So that's why we apply the steady state approximation. Okay, so this is an important concept. Now let's go back to the parallel reaction. So parallel reaction means so from the reactant molecule, let's say A, to form the product molecule. So there are two possible pathways are there. So like different possible pathways are there to form different product molecule. That means mainly the reactant molecules can participate in different pathways to form different product molecules. So let's say it is like it like A molecules, the reactant molecules can go or can follow this pathway to form the product B molecules, or A molecules can follow this pathway to form the C molecule. So rate constant for this pathway, let's say K1, and rate constant for this pathway, let's say K2. So that's why we call it parallel reaction. Why parallel? Because reactant molecules can form different product molecules by following different reaction pathways. So that's why we're calling it parallel reactions. Okay. Now similarly, like initially at t equal to 0, no B and C will be there, so only A. So let's say initial concentration is A0, and with time the B and C molecule will also form, right? Now the rate of formation of B molecules, rate of formation of B molecules, which will be equal to the rate of disappearance of A molecules with this pathway, right? With this pathway. Rate of disappearance of A molecules, which will be just minus of dA dt, which will be equal to rate constant for this pathway K1 times concentration of A, right? Similarly, which will be equal to just a dB dt, the rate of formation of B molecules. Similarly, minus dA dt, which will also be equal to K2 times A for this pathway, right? Which will be equal to dC dt. Means the rate of formation of C molecule. Now let's say this is equation 1 and this is equation 2. From equation 1 and 2, the overall reaction you can just write down here. dA dt, the total rate of disappearance of A molecules will be K1 plus K2 A, right? For both these pathways. This is overall rate equation. Now you can just integrate here and you can just write down or find out the concentration of A with time, which will be equal to concentration of A at time 0 times e to the power minus K1 plus K2 times T. Okay, you can remember it. Now you can just find out also the concentration of B molecules and with time and C molecules with time also, like from this equation dB dt equal to K1 times A, right? And you know the dB dt equal to now K1 times A0. We know the expression of A, just put it here, A0 times e to the power minus K1 plus K2 times T, right? So from here you can just get by integrating concentration of B also. So this is actually K1 times A0 by K1 plus K2 times 1 minus e to the power minus K1 plus K2 T. So this is concentration of B molecules with time. Similarly for C molecules, you can just, which will be K2 times A0 times K1 plus K2, then 1 minus e to the power minus K1 plus K2 T. Now importantly, for this parallel reaction at time, any time t, the ratio of concentration of B and C, that means ratio of different product, so concentration of B and concentration of C. So if you just divide these two equations, you will get all these terms will be cancelled. You will get just K1 divided by K2, right? So this is a very important thing. Like for parallel reaction, the product ratio of different products, concentration of different products, which will be equal to just their rate constant, ratio of their rate constant. So K1 divided by K2. Okay, now let's say for this reaction from A to B, from A to C, then A to D. So this is also a parallel reaction, right? The three possible pathways are there. Here the concentration of B divided by concentration of C, let's say this is K1, this is K2, this is K3. So it will be just K1 divided by K2. Okay. Now also the concentration of C divided by concentration of D, which will be equal to just K2 divided by K3. and also then the concentration of B divided by concentration of D at any time, which will be just K1 divided by K3. Okay, so different product ratio which will be equal to just the ratio of the rate constant. Okay, now let's consider this reaction A to B, then A to C, K1, K2, and let's draw the graph here for parallel reaction. So this is concentration, this is time. So first, initially at time t equal to 0, there are no B and C molecules, only A molecules are there, so that it's a concentration, let's say A0. So this is A0. So with time the A molecules will decrease, so concentration of A molecules will decrease, right? Now the concentration of B and C molecules will form through different pathways, different reaction pathways. So with time the concentration of B and C molecule will form, just like this, B and C molecules will form by following different reaction pathways. So this is actually C, so this is actually B, this is actually A. Okay, now at any time, let's say this time frame, concentration of A plus concentration of B plus concentration of C, which will be equal to initial concentration A0, and the concentration of B divided by concentration of C, which will be equal to just K1 divided by K2. Okay, these two are very important information. Okay, so this is parallel reaction, and the third is the reversible reaction or opposing reaction. Okay, reversible or opposing reaction. Reversible reaction means, let's say from reactant molecule A are forming B, and B is also forming A molecules, like opposite reaction. So rate constant, let's say for A to B is K1, and from B to A, let's say K minus 1. So this we call the forward reaction, and this we call the backward reaction or reverse reaction. Okay, let me just check once. Yeah, now for reversible reaction, that means the A and B molecules are in equilibration. Okay, that means the overall rate constant, which we call the K equilibrium, which is K1 divided by K minus 1. Okay, so the equilibrium constant for this reaction will be just K1 divided by K minus 1, which will be equal to the concentration of B divided by concentration of A. So this is the equilibrium constant. Equilibrium constant. Now let's say for let's do an example. Let's say this type of reaction is given, reaction scheme is given, where the rate constant for A to B is K1, from B to A is K minus 1, and B to C is, let's say, K2. Now you are asked that to find the rate equation for this reaction scheme, where we have given the concentration condition K minus 1 is very greater than of K2. With this condition, that means K minus 1 is very greater than of K2, means B to A reaction step is happening fast compared to the B to C reaction step. That means when A to B molecules are forming, then there are two possibilities for the B molecules, right? It can form C molecules here from there, or it can go back to A molecules, right? Now this B to K2 less than K minus 1 means this step is happening much slower compared to this step. That means for first A to B molecules are forming, then B to A molecules are forming very fast compared to this step. That means these A and B molecules, we can say, are in equilibrium with each other, right? So we can say they are in equilibrium. With each other. So let's say the equilibrium constant is K equilibrium, which will be just K1 times K minus 1, which will be the concentration of B divided by concentration of A, right? Now the rate equation, that means dc dt, rate of formation of C with time, which will be equal to K2 times B, right? K2 times concentration of B. Now we know we can get the concentration of B expression from this relationship. So the concentration of B will be K1 times concentration of A divided by K minus 1, right? So it will be K1 times concentration of A divided by K minus 1. So it will be just K1 K2 by K minus 1 times A. So the rate equation will be just K1 dc dt will be K1 K2 by K minus 1 times concentration of A. So like this, with this proper condition, you have to just find out the rate equation. Okay. Now if the conditions were like this, let's say K2 is greater than, very greater than K minus 1, let's say with this condition, that means when A to B molecules are forming, B to C are forming very fast compared to B to A, right? That means with this condition we can say that the intermediate B are very transient in nature, so we can apply the steady state approximation for the B molecule. Okay, that means we can apply this condition dB dt, which will be equal to 0. Now by applying with this equation we can get the right rate equation. Let's do that. So it is important actually. This is K1, this is K minus 1, this is K2. Now let's say the condition is K2 is very slow, K2 is very fast compared to K minus 1. Okay, now with this condition we can apply steady state approximation for intermediate B equal to 0. Now let's first write down each and every rate equation. Okay, so dB dt for this reaction scheme will be K1 times A. So from A molecules with rate constant K1, B molecules are forming, so K1 times A. Then with rate constant K minus 1, it is also disappearing, so that means minus K minus 1 times concentration of B. This minus sign means the concentration of B disappearing. Again with rate constant K2, the concentration of B decreasing or disappearing, then minus K2 times concentration of B, right? Now this is equal to 0 with steady state approximation. That means K1 times A, then minus B common, K2 plus K minus 1, right, equal to 0. Now let's find out the concentration of B here. So B will be K1 times A divided by K minus 1 plus K2, right? So this will be concentration of B by applying steady state approximation. Now with this reaction scheme, the proper rate equation will be the final rate equation equal to dC dt, rate of formation of product, which will be equal to K2 times B, right? So dC dt will be K2 times B. Now we can replace B here. It will be K1 times A divided by K minus 1 plus K2. So it will be K1 K2 by K minus 1 plus K2 times concentration of A. So here the proper rate equation will be this, with this condition, K2 first term, then K minus 1. Okay, so like this you have to just apply different condition like steady state condition or equilibrium condition to find out the proper rate equation. Okay, so any doubts up to this? Okay, so then we can just move forward. Okay, then let's discuss the transition state theory. So transition state theory, so there are actually to find out the proper rate expression for any chemical reactions. So there are many theories, so we have to first make different assumptions, and depending upon different assumptions there are many theories. So first one is the collision theory, and second one is the transition state theory, third one is the RRKM theory. Like there are depending upon different assumptions, so there are different theories. Okay, now let's discuss the transition state theory. So because this is important, TST. So in TST we first assume that first the reactant molecules actually combine together or interact together to form a activated complex, right? Then from that activated complex the product molecules will form. So first assumption is that activated complex or transition state, activated complex. So activated complex means, so first the reactant molecules come together or interact each other and form a type of complex which we call the activated complex, and from that activated complex the product molecules will form. Now the schematic representation is like this. let's say these are the reactant molecules here, and here let's say this is product molecules, and first, and this is the transition state or activated complex. So this is represented by double dagger. This we call the transition state. Okay, now let's first from A, reactant molecules A, it will form the transition state, which will be just A double dagger. Then from the transition state or activated complex, the product molecules are forming. Okay, now in the TST approximation, TST theory, it is approximated or assumed that the reactant molecules, that means R, and the transition state complex or activated complex are in equilibrium. They are in pre-equilibrium with each other. Okay, so it is assumed in the TST. This activated complex A star and the reactant molecules are in equilibrium with each other. That means there will be an equilibrium. Let's say this is K1, this is K minus 1, let's say this is K2. So these two species are in pre-equilibrium. With each other. Okay, now in the transition state theory, the main rate expression is, rate constant is K equal to kBT divided by H times K double dagger, which is K double dagger. I am explaining this. So K is the main final rate constant for this reaction. K double dagger is the equilibrium constant. Equilibrium constant for this step A to A double dagger. Okay, for this step, this is the equilibrium constant for this step. Kb is the Boltzmann constant we know, T is the temperature, and H is the Planck constant. Okay, so this we call the Eyring equation. That means if you can just so K will be equal to kBT divided by H, and equilibrium constant we can write e to the power minus delta G double dagger divided by RT, right? We can write any equilibrium constant equal to exponential minus delta G double dagger divided by RT. So delta G double dagger is the free energy of activation free energy for which step? For this step, A to A dagger double dagger. Okay, this is the activation free energy. Now from thermodynamics we know that the delta G equal to delta H minus T delta S, right? So delta G double dagger will be delta H double dagger minus T delta S double dagger. So this is the enthalpy of activation, this is entropy of activation. Okay, so for this expression we can write K equal to kBT by H exponential minus or plus delta S double dagger by R times exponential minus delta H double dagger by RT, right? Okay, so rate which is K, this is actually rate constant. K will be equal to some pre exponential factor, like let's say A times e to the power minus delta H double dagger by RT. Now sometimes we associate delta H double dagger with the activation energy, but in general it is not true. I will discuss in the next class. So this is A is called the pre-exponential factor. Let's, this is EA by RT. EA is the activation energy. A is the pre-exponential factor. Okay. Now this equation we call it Eyring equation. From the overall derivation is called the Eyring equation. Now here pre-exponential factor is actually temperature dependent. If you just look at kBT by H, here this term is there, right? kBT by H. So here T is there. So here pre-exponential factor is actually temperature dependent. And how it is dependent upon temperature? Proportional to temperature T, right? So it is important in transition state theory or in Eyring equation, from Eyring equation, the pre-exponential factor AT, which is temperature dependent, and it is dependent on temperature with T, like the proportional to T. So this is important. And another empirical expression is Arrhenius equation, right? We all know that Arrhenius equation, where we write down K equal to A times exponential minus EA by RT. So Arrhenius actually told that the reaction will happen. So reaction mechanism is, first the reactant molecules will form some sort of activated complex, then from the activated complex product molecules will form. So empirically or by experimental data, he actually fitted this equation. K times, K is the rate constant, A is the pre-exponential factor, EA is the activation energy, R is the universal gas constant, T is the absolute temperature. Now here A is just a constant, not temperature dependent, but proper Eyring equation from transition state theory, by deriving this, you can see in TST the pre-exponential factor AT is temperature dependent. Okay. Now by comparing the Arrhenius equation and the Eyring equation, we can get the relationship between the enthalpy of activation, internal energy of activation, and the proper activation energy EA. So I will discuss in the next class, and I will discuss also the collision theory also. Okay. So today I think this is fine. So let me just ask if you have any doubts. So any doubts or any questions?
No, sir.
Okay, so is it fine? All? Yes, no?
Yes, sir. Fine.
Okay. So today I'll just signing off. Then in the next class we will discuss how we can get the relationship between the enthalpy of activation and activation energy by comparing the Arrhenius equation and the Eyring equation, and also we'll discuss the collision theories also. Okay, so see you in the next week. Okay, bye. I'm just signing off today. Bye.